Okay, for 3D rigid body equilibrium, there's really not a whole lot new, just an extra layer of complexity having 3 dimensions. The procedure is exactly the same in that you draw a free body diagram. Remember, you've got to include all of your external forces as well as all of any supports that you have. And in dealing with the supports, remember that if it restricts translation in a certain direction, then there's got to be a force in that direction, okay, keeping it from moving in that direction. Okay. Likewise, if it restricts any sort of rotation, there has to be a couple moment, okay, that you have to include in the direction that is restricted. So it may be able to rotate around one axis but not another. Whichever axis it's not allowed to rotate about, there needs to be a couple moment about that axis restricting that motion. Okay, so again, restriction of motion leads to a support reaction. And that needs to be included on your free body diagram as well as any other external forces. Once you have all the forces drawn on the body, go ahead and, since we're in 3 dimensions, go ahead and write each form or each force into Cartesian form. So you have all the x, y, z components of each force. Once you get that, then you go ahead and apply your equilibrium equations. Now we're going to have some of the forces in the x, some of the forces in the y, and some of the forces in the z all equal to 0, just like we did with 3D particle equilibrium. However, this is a rigid body, so we can also have the potential for rotation. So we'll have moments. Okay, so we have the sum of the moments equaling 0, and that's going to be the sum of not only the couple moments, but also the moments of any forces, any r cross f's. Okay, notice this is a vector equation. Okay, so we'll actually get 3 more equations out of this, but I'll talk about in just a second why we use the vector form of that. Okay, but before we do that, make sure you choose point O, okay, appropriately. And there's really 2 choices that you can help make what point you choose to take the moment about. The first is, just like in 2 dimensions, choose the point with the most unknown forces at. Then a lot of the unknown forces don't show up in your moment equations and make them much easier to algebraically solve. Okay. The other thing you can do is realize that I'm going to have to do a 3-dimensional cross product and choose a point that makes a very simple moment arm, maybe a 1-dimensional moment arm, in my r cross f part of the equation, that will make that cross product much easier to deal with. Okay, which will make, so it's just a trade-off which is easiest to deal with. Be it get rid of a lot of unknown forces or make really easy cross products for yourself. Okay. So once you've chosen that point, go ahead and perform the 3D cross product, as opposed to with some of the forces where we split everything up. In 3 dimensions, it's a lot easier to do the cross product in 3 dimensions. So you've got this r vector cross f vector. Okay. After you've done the 3-dimensional cross product, you then separate it out into the x, y, and z components, and the sum of the moments in all directions have to be 0. Okay, but again, it's generally easier to deal with the moments as one vector first and do a 3-dimensional cross product and then separate out into the components. And what that's going to leave you with is 6 total equations. 3 force equations as well as 3 individual moment equations in each of the 3 directions. That means you can solve up to 6 unknowns in this equation. So again, procedure is the same. Free body diagram, write your forces, apply the equilibrium equations. Really, the main difference here is the fact that you have up to 6 equations that you can solve unknowns for.